Let's just dive right into this. You are on a rock, floating in space, surrounded by more rocks, and gas, and, well, a whole bunch of nothing mainly. Oh, and look at that. The rocks are actually going around the gas. What the heck is going on here? To understand how this cosmic magic works, we need to lay down some foundational physics.
Which brings us to part 1. Welcome to the rock. We're predicting the predictable with Isaac Newton.
To figure out what kind of magic actually keeps our rock spinning, we've got to go back in time and meet our main gravity guy, Sir Isaac Newton. You see, classical physics, the stuff Newton figured out, lulls us into this wonderful false sense of security where the math is perfectly predictable. One of the absolutely most important things he gave us is the equation F equals ma, force equals mass times acceleration. A force is really just a push or a pull. Mass is how much of something there is, and acceleration is just how fast the velocity is changing. So the crucial point here is that if you apply a force to a fixed mass, you get a highly predictable amount of acceleration. If you know all the forces acting on a basketball midair, you can predict with 100% certainty if that ball is going to drop perfectly into the hoop or smash right through your neighbor's windshield. Now legend has it, an apple fell on Newton's head with a comical bonk, prompting him to realize that masses actually attract one another. And yes, even you, no matter how small you might feel, attract pretty much the whole universe, at least a little bit. He put this on paper as the law of universal gravitation, which includes the inverse square law. Basically, a bigger mass means a bigger pull, but a bigger distance means a much smaller pull. As distance increases, the force shrinks by the square. This centripetal force is exactly what keeps the planets endlessly falling towards the sun, but moving just fast enough to constantly miss it. And you know, this actually clears up a massive misconception. Mass and weight, they are not the same thing. Mass tells you how much of a biological blob you are. Weight is the force of gravity that your blob actually feels. Your mass would be the exact same on Earth as it is on the moon, but the weight you perceive would completely change because the moon has a much weaker gravitational pull. So hey, the good news is you aren't overweight, you're just on the wrong planet with the wrong gravitational pull.
Moving right along to section 2, energy, work, and heat, or as I like to call it, dropping phones and breaking things.
Let's see how this builds into something we've all experienced, breaking things. If you've ever dropped your smartphone and just watched in horror as the screen shatters, you've witnessed energy in action. Energy, which is measured in joules, is just a property of a thing. It doesn't have a direction like force. It's just a number chilling there, waiting to do something. When you're holding your phone, it stores potential energy simply because it's being held up. When you drop it, that potential energy is rapidly converted into kinetic energy, the energy of movement. But what about work? Well, in physics, work is only done when a force is applied over a distance. So if you're struggling and sweating at the gym to lift a massive barbell, but it doesn't move a single inch, I hate to break it to you, but your feelings of exhaustion are invalid in the face of physics. Zero distance mathematically means zero work.
Okay, so let's dive into the conservation of energy. Energy absolutely cannot be created or destroyed, it can only be converted. So when a moving car hits the brakes and stops, where does all that kinetic energy actually go? It turns into heat. Friction between the brakes and the wheels creates heat, which dissipates and makes the surrounding air molecules wiggle faster. And that average kinetic energy of wiggling atoms, that is exactly how we define temperature.
All this hot air brings us to thermodynamics and an honestly terrifying concept called entropy. Entropy is basically the absolute mess of disorder in a system. Just imagine a beautifully structured ice cube sitting out in the sun. The sun obliterates it into a puddle of water. The system just went from neatly organized, low-entropy ice to chaotic, high-entropy water that can take on countless shapes. The whole universe is on an unstoppable path to higher entropy, which is exactly why a broken egg doesn't unbreak and why time only moves forward.
All right, on to section 3, the electromagnetism magic, opposites attract and induction shocks. Let's shift gears here and talk about the invisible magic of electromagnetism. Objects have a charge, positive, negative, or neutral. Opposites want to cuddle, and like charges just repel each other. Coulomb's law for these electric charges looks suspiciously exactly like Newton's law of gravity in disguise, just applied to tiny charged particles instead of massive planets. Electrons carry a single negative charge, and when they flow through a wire, we get electric current. We can describe this flow really rapidly with 3 rules. Current is the amount of electrons passing through. Voltage is the difference in electric potential. Think of it as the downhill push that forces those electrons to move. And resistance is, well, it's exactly what it sounds like. It resists the flow. And then we have Maxwell's freaky equations. Now, I know they look completely terrifying on paper, but they really just tell us that electric fields and magnetic fields are deeply connected. A static charge creates an electric field. Magnetic poles are never lonely. You literally cannot have a North Pole without a South Pole. But here is the freaky part. Moving a magnet creates an electric field out of thin air, and moving a charge creates a magnetic field. This whole process is called induction, and it's literally the reason your phone charges on a wireless pad without actually plugging it in. The moving magnetic field in the pad makes the electrons in your phone go absolutely crazy.
Next up, section 4, atoms and radiation, the tiny and the deadly.
Let's shrink down even further now, past those invisible fields all the way down to the atomic level. If we look at water molecules, they're made of atoms, and atoms consist of a super dense core surrounded by this buzzing cloud of electrons. Welcome to the standard model. That dense core is made of protons and neutrons, which are made of even smaller particles called quarks, with quirky names like up, down, strange, and charm. If you change the number of protons in a core, you get an entirely different chemical element. But if you just change the number of neutrons, you get an isotope. And the thing is, most isotopes are overweight and highly unstable, so they fall apart, releasing ionizing radiation, which, not so fun fact, will absolutely kill you.
Now, even though individual atomic decay is totally random, if you have a massive group of unstable atoms, you can actually predict exactly how long it takes for half of them to fall apart. This is known as the half-life. But before we get totally bogged down in radioactive decay, we need to suddenly accelerate our narrative to talk about the absolute fastest thing in the entire universe.
Which brings us to section 5, Einstein bends space, unraveling the fabric of reality.
Historically, pretty much everyone thought light was just a wave. And why wouldn't they? Because if you shoot light through 2 tiny slits, the beams cross and create a classic interference pattern, where the waves either add up or cancel each other out. And this brings us right to the very edge of our reality-breaking territory. Light travels at a completely constant speed in a vacuum, exactly 299,792,458 meters per second. And this brilliantly sets the stage upon which a guy named Albert Einstein completely changed the game.
So Einstein essentially looks at classical physics and says, nah, scratch that. Everything you know is wrong. He discovered that light actually comes in tiny individual packets called photons. Furthermore, he assumed the speed of light is completely constant for everyone, no matter how fast you're moving. If you're on a speeding train and turn on a flashlight, someone standing still outside doesn't see the light moving any faster. It's the exact same speed. The only mathematical way this works is if time itself passes slower for the person on the train. If the speed of light is constant, time itself absolutely must be relative. Einstein also realized that energy and mass are, well, kind of the exact same thing, giving us the famous E equals mc squared. He showed that you can split a heavy nucleus apart, that's fission, or smash smaller nuclei together, which is fusion. In both cases, the resulting nucleus is actually slightly lighter than the starting ingredients. That tiny missing mass defect doesn't just disappear, it gets converted into a humongous amount of raw energy. That is exactly what makes atomic bombs go boom. And finally, Section 6. Welcome to quantum chaos, where reality is highly suspicious. So by proving light was a particle, Einstein accidentally birthed a field of physics that he personally thought was a giant hoax. Quantum mechanics. Pioneered by Max Planck, who agreed that all energy comes in tiny packets called quanta, this is the final, most chaotic stage of our physics explainer. In the quantum realm, the rules make absolutely no sense. An electron isn't just in one place, it's here, there, and everywhere at the exact same time in a state called superposition. We can only use Schrödinger's equations to map a probabilistic cloud of where it might be. And thanks to Heisenberg's uncertainty principle, particles guard their private data really closely. If you take a sharp photograph to see a particle's exact location, its speed becomes a complete blur. You can literally never know both position and speed at the same time.
Which brings us to the ultimate mind-bender of this whole explainer. Remember that double-slit experiment where light waves interfered with each other? Well, physicists fired single individual photons through the slits one at a time, and over time, they still created a wave interference pattern on the wall. How is that possible? What did a single particle interfere with? The math suggests the single particle literally interfered with itself, acting as a wave and going through both slits at the exact same time.
Okay, the physicist said, let's just put a measuring device next to the slits to see which one the particle actually goes through. But the moment they tried to measure it, the particle stopped acting like a wave. The interference pattern completely disappeared, and the photon chose to go through just one slit, acting like a normal boring particle again. The mere act of observing it literally changed reality. Highly suspicious, right? It leaves you wondering, does reality only exist when you try to measure it?